k is 1, what do we have? This O'Brien?
1 over 2k minus 1, or 2 to the first minus 1.
Right. And when k is 2, what do we have?
1 over 2 to the power 2 minus 1.
And when k is 3, what do we have?
1 over 2 to the power 3 minus 1.
Oh, you also were up late last night, huh? 2 to the power 4, yes. Etc., etc., etc. Now, can I use it, compare this with the geometric series with common ratio 1/2? No, because I'm dividing by something smaller. I'd like to compare it with 1 over 2 plus 1 over 2 squared plus 1 over 2 cubed plus 1 over 2 to the 4 plus 1 over 2 to the 5, which converges or diverges? It converges. It is a geometric series with a common ratio of 1/2. You also out late, Mr. Harris? Converges. Because this is a geometric series with a common ratio.
1/2.
Well, there's a big difference. One is bigger than 1 and 1 is less than 1. Which one is it?
1/2.
Okay. Converges or diverges?
Converge.
Converges. Now, can we conclude that this converges using the comparison test? Not quite. Because what do we say about this? Smaller or bigger than that? It's bigger. And what about this and that? Bigger. Can we use the comparison test?
No.
Logic is short. This converges, and these are term by term bigger. You may conclude nothing. Dang. But I know that this converges. Why? Because eventually you will have 2 to the power
Infinity.
70 minus 1. What's 2 to the power 70 minus 1?
No. Really small.
2 to the power 70. And what's 2 to the power 71 minus 1?
2 to the power 7. Or 1 over.
2 to the power 71. So eventually these two are really the same. Eventually. So this is convergent. What I'm trying to say is that this starts to look like a geometric series with a common ratio of. It starts to look like a geometric series with a common ratio of 1. That is when I is very big. 1 over 2 to the 16 minus 1 plus 1 over 2 to the power 17 minus 1, which is really 1 over 2 to the 16, which is really 1 over 2 to the 17. What's the common ratio? 1/2. Because this is much smaller. And this is what? Much smaller than this. You have to use your neurons. That is to say, if you look at the ratio of the elements, you go far enough, does it look like a geometric series? If so, what is the ratio? Bigger than 1? Diverges. Smaller than 1? Converges. This is called the ratio test. If, when you go far enough and you look at the ratio of the succeeding and the successor, previous and the succeeding, the previous and the succeeding, previous and the succeeding, it starts to look like a geometric series. And then you say, well, what's the common ratio? If the common ratio is less than 1, it's going to converge. If the common ratio is bigger than or equal to 1, it's going to diverge. It's like that down. This is called the ratio test. The most important test of all. And let us assume again we have a non-negative sequence. Okay? We'll talk about negative sequences later on. Assume you have a sequence, AI, and assume the sequence is non-negative. all the terms are not never negative. No term is negative. So I don't have to worry about absolute values. Now look at the ratio eventually. The 101 divided by the 99 1. The 101, 1 divided by the 101. This is the protein that fixing on 1/2 or 2/3. In the limit, what is this ratio going to? Let's say it goes to some number 2/3. If that number r is less than 1, if r is less than 1, the series, then the series converges. If the ratio is bigger than 1, then
Divergence.
the series diverges. Well, there's one case I haven't looked at. What case is that?
If n equals +1.
What may we conclude when r equals 1?
No.
The test fails. Says you have to try something else. Can't help you. Dang. This will happen quite often. Test inconclusive. A more appropriate word is fails. Let's do some examples. So here's one.
Test as well.
Huh? Test is, oh, well, now I'm interested. Test is, test is failing. Test is failing. Test is inconclusive. Inconclusive. Or shall I say, if r is equal to 1, try something else.
Dang.
Gang. Okay, here's an example. Now, what kind of series is this, Mr. Harris? Who knows? Who knows? It's certainly not an arithmetic series. It's most certainly not a geometric series. It is most certainly not a P series. It is most certainly not a harmonic. Who knows? But there is something weird going on here. As I is getting big, this is getting big. Huh? There's a linear function like 3x plus 1, and 3x plus 1 goes to infinity. And as I is getting big, this is getting big, like 2 to the power x. Dang. The numerator is getting big, the denominator is getting big. Who's winning? Who's winning?
In the bottom.
Why? Because he's exponential, and the top linear. So most certainly the terms are going to go to 0. You can prove it. You will have to use
Divergence.
L'Hopital's rule. Yes! What are the AIs? 3i plus 1 over 2 to the power I. What is the limit as I goes to infinity of 3i plus 1 over 2 to the I? Or if you want, you can change it to x. Infinity over infinity. You'll have to differentiate this and differentiate this, and then the I. See, it would be Some number over infinity. What's some number over infinity? 0. You say what? Damn, divergence test failed. The terms are going to 0. That is to say, this guy is dominating, sucking him down to 0. The question now becomes,
There's no test.
is it fast enough? And the answer is yes. Now, most certainly, this is not a geometric series. Let me convince Mr. Harris. First term, Mr. Harris.
3 times
3 plus 1 over 2 to the first.
4 over 2 in the next one.
7 over 4.
And the next one.
10 over 8.
And the next one.
13 over 16.
And the next one. Mr. Harris, are you convinced this is not a geometric series?
Yes.
Thank you. But my hunch is that eventually it starts to behave like a geometric series with a common ratio of 1/2. That is to say, this guy starts to dominate eventually. It says, yeah. But we'll do that using the ratio test. Let's use the ratio test. What is AI?